Okay, so in your textbook at the very end of chapter 2, you will find some information about the various point groups, what they're called and how to identify them, what do they look like. And basically there's this sort of complicated decision table, decision tree map that lets you decide which point group a molecule belongs to. So, you take your molecule and you say, okay, is the geometry linear? If it is, then it has to be either in the point group D infinity H or C infinity V, depending on whether or not it has inversion symmetry. Okay, and I'm not going to go through this whole table, but you can look at this on your own. And then there are also some examples given at the very end of chapter 2 of some different point groups. And point groups have a name that's given in a notation called Schoenflies notation. And so if a molecule is planar, or if it has just one symmetry plane and no other symmetry operation, right? This would apply to every planar molecule, basically. Then it's said to be in the CS point group. If it has only one center of symmetry, such as this molecule shown here, and no other symmetries other than identity, then it's said to belong to the CI point group. If there's just a single n-fold rotational axis of symmetry, then it belongs to the C sub n group. So a C sub 1 molecule would have no elements of symmetry, right? Because C1 would rotate 360 degrees. C1 is the same as identity. Or if you have a C3 axis, just a C3 axis, then the point group would be called C3, and so forth. Some other very important point groups. I'm not going to go through all of these right now, but one that you'll encounter very commonly is CNV. We already encountered 2 examples of that today, right? Water is C2V and ammonia is C3V. And a CNV molecule has one CN axis and n sigma V planes, right? That contain that principal rotational axis. Another important one is called CNH. That's if you have one CN axis and a sigma H plane. An example of that would be 1,2-dichloroethylene, right? You can see it has one C2 axis that comes out of the plane of the page, right? That rotates basically this chlorine 180 degrees onto that chlorine, and so forth. And then it also has a plane of reflection in the plane of the board. Another very common one is DNH. A DNH point group, a molecule with this type of symmetry, has one principal CN axis. So an example is benzene. Benzene would be D6H. It has one CN axis, right? In this case, coming out of the plane of the board, out of the plane of the page. It has n different C2 axes that are perpendicular to that. So basically, you can rotate 180 degrees by this axis, right, by this axis here, right, by this axis here, etc. There's 6 of those possible axes. And it has one sigma H plane. So there's a plane of reflection in the plane of the board. Okay, I'll just skip ahead a little bit because some of these point groups you're not going to see so often that you should be aware of them. You can take a look in your textbook. Another couple that are very important are what's called the tetrahedral group, the T sub D group. This would be the point group of methane. Methane is highly symmetric. It has many symmetry operations, but anything with a tetrahedral geometry like this, right, with 4 equivalent substituents, that would have TD symmetry, and something with octahedral symmetry, such as SF6. Right, this is another very highly symmetric point group with many symmetry operations. It belongs to the point group called O sub H, right, which we call the octahedral group. Okay, so you can take a look at that in your textbook. And I'm going to go ahead and continue a little bit. I'll just get started on the next chapter. And then we'll finish up the next chapter next week. Whoops. You can fast forward this part. Okay, so far we've been talking about groups of symmetry operations in terms of physical operations that were acting on molecules, right? So reflections, rotations, and so forth. But we can also represent these symmetry operations using matrices. And so the next topic is going to involve the matrix representation of groups. Okay, so first just a little bit, and this is basically chapter 3 of Bernath, if you want to follow along reading. Okay, and just to review some special properties that matrices can have. We talked a little bit about matrix algebra last time when we talked about MATLAB, right, when we gave the MATLAB tutorial. I'm assuming that you've had an introduction to linear algebra and to matrix, mathematics involving matrices. If it's been a while and you've forgotten, you can look at the first section of Bernath, chapter 3. I'm not going to go through all the details right here. But you can read the first section of chapter 3, and it gives a very nice refresher. It gives you all the basics about matrix multiplication and matrix operations. Okay, but there are some special types of matrices that I want to just refresh you about. So a review of some special matrices. Marker is not very good. Let me switch to a different one. Maybe this one's gotten better. Yeah, that one looks pretty good. Okay, so the identity matrix is called I, and it has the property that the ijth element is given by a Kronecker delta. So if I equals j, then it's 1, otherwise it's 0. So this matrix has 1s along the diagonal and 0s elsewhere. A matrix is said to be symmetric if it's equal to its own transpose. So if a matrix A, if the transpose of A is equal to itself, then it's symmetric. And so in this case, the matrix would be symmetric if, for every I and j, if Aij is equal to Aj. Okay? If you have a complex matrix, then most of the time you don't care so much if it's symmetric. What you care about is whether it's Hermitian. So this is kind of the complex analog of a symmetric matrix. And a Hermitian matrix is a matrix where the Hermitian transpose, right, or the conjugate transpose of the matrix is equal to itself. And the conjugate transpose just means you transpose the matrix, and then you take the complex conjugate of each element. Right? So that would mean that Aij would equal the complex conjugate of Aji. Okay? A matrix is said to be orthogonal if the inverse of the matrix is the same as the transpose of the matrix. So if the transpose of the matrix equals the inverse, then it's orthogonal. And if that's the case, then if you multiply the matrix by its transpose, then of course you're going to get the identity matrix. And again, sort of the complex analog of an orthogonal matrix is called a unitary matrix. And a unitary matrix has the property that if you take the conjugate transpose, then you get the inverse. And so in this case, a dagger times A would give you the identity matrix. Okay? And unitary matrices have a very special property, and that is if matrix A is unitary, then if you take the matrix A, I'll show you it's a matrix by using 2 underscores. If it operates on a vector V, I'll represent that this is a vector using 1 underscore. Then the magnitude of A operating on the vector V is the same as the magnitude of the original vector V. So basically, this unitary matrix changes only the direction of the vector. It does not change the magnitude of the vector. And in point group theory, all of the symmetry operators are going to be unitary operators because they only change, how the molecule is oriented in space. They don't change the size of the molecule, right? So they don't change the bond lengths. Right, so molecular symmetry operators are all going to be unitary. Okay, and you can define a similarity transformation for matrices, just the same way that we defined a similarity transformation for symmetry operators. So similarity transformation is a transformation where you use a transformation operator Z, and you operate the inverse of Z from the left and Z from the right, and that transforms you to some other matrix B. Right, so this is a similarity transformation. And if Z happens to be unitary, then this is a very special type of similarity transformation called a unitary transformation. Okay. Okay, and one final important concept is the trace operator. So the trace of a matrix, which is denoted TR of the matrix, let's say A. The trace is just equal to the sum of all of the diagonal elements. And if the matrix A and the matrix B are related by a unitary transformation, then the trace of the matrix A is going to equal the trace of the matrix B. Okay, so I'll cover just one more topic today, and that is how to represent these, basic matrices. So these operations that we've talked about, these symmetry operations, if they act on just a point in space, x, y, z, how can you, or a vector in space, x, y, z, how can you represent those symmetry operations, right, reflections, rotations, etc., using matrices. Okay, and so first, so first of all, so we're going to talk about symmetry operators. And position vectors. Okay, so let's say we have some position vector. It gives the coordinates x, y, z, or it has the elements x, y, z. We can also use the same notation that we used before at the beginning of this course, where we just call the x-coordinate x1, the y-coordinate we'll call that x2, and the z-coordinate we'll call that x sub 3. Then we could also denote this vector using this notation, right? So it's just the length of along x times the unit vector in the x direction plus the length along y times the unit vector in the y direction, etc. Okay, and then we're going to apply symmetry operations to a vector like this. Okay, so first, let's think about reflection. And if we reflect a vector along the xz plane, right, the 1, 3 plane, right, if we do this operation on x1, x2, x3, right, x, y, z, then we're going to basically invert the y coordinate, right? So we're going to map y onto minus y. And the matrix that would accomplish this equivalent operation would be, it would have to look like this. Right? So if you operate this matrix on x1, x2, x3, you can easily prove to yourself that this is going to equal x1 minus x2, x3. And so we would say that the matrix operator that is equivalent to the 1, 3 reflection, that's going to be a matrix that looks like this. And by similar arguments, you can show that if you have a reflection across the plane containing the x and z axes, then that one is going to look like, we already did xz, but I want xy. Right, the xy plane. That one is going to multiply the z coordinate by -1. So the matrix for that is going to look like that. And if we reflect about the yz plane, I'm sorry, d for sigma yz, that's going to multiply the x coordinate by -1. Okay? So these are the matrix representations of these different reflection operators. Okay, how about rotation? Okay, if you rotate by an angle theta about the z-axis, x3, then that gives you some new vector, x1 prime, x2 prime, x3 prime. And it's easy to show that the new value of x1 is going to be, or the new value of x is going to be x times cosine theta plus y, right, x2 times sine theta. The new value of x2 is going to be minus x1 times sine theta plus x2 times cosine theta. And rotating about the x3 axis is going to leave the x3 coordinate unchanged. So this is going to be just x3. Okay? And the matrix then that would accomplish the same transformation would have to look like this. It would have to look like cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1. Right, so if you multiply this matrix by this vector, you can prove to yourself that you get this rotated vector. Okay? And you know, the inverse of this vector, so this would be d, this would be the vector, I'm sorry, this would be the matrix that represents the c theta operation about x3. And the inverse of that that would be just the matrix that operates, where you replace theta by minus theta, right? And cosine of minus theta is equal to cosine of theta, right? Because cosine's an even function. Sine of minus theta equals minus sine of theta, because sine is an odd function. And so you're going to get this matrix here. This would be the matrix representation of c theta x3 inverse. And you can indeed show that if you multiply this matrix together with this matrix and use trigonometric identities, you get the identity matrix. Okay, and you can also see that this matrix and this matrix are indeed the transpose of one another, which according to our rule over here shows you that you know, if the conjugate transpose of the matrix is the same as the inverse, then it must be a unitary matrix. So these are indeed unitary matrices, right? Unitary operators. Okay, I'm going to just write down a couple more matrices and then we're going to be done. Okay, so the inversion matrix, or the inversion operator, I, this operates on a vector x, y, z, and it maps x to minus x, y to minus y, and z to minus z. And so the matrix representation of that operator is going to be a diagonal matrix with -1 along the diagonal. Right? You can easily prove to yourself this times this vector is going to equal this vector. Okay, the next one, so this is inversion, and then the next one is the rotation reflection, right? The improper rotation. So if you have a improper rotation, S theta x3, right? So this rotates by an angle theta about the x3 axis, and then does a reflection in the plane that is perpendicular to the rotation. So it would do a reflection in the xy plane. So this is actually, we can derive the matrix from this by just multiplying together the matrices for those two operations. So first, we do a C rotation by an angle of theta about the x3 axis. Then we apply a sigma 1, 2 reflection. Okay, and if you multiply the matrix representations together for those two operations, the 1, 2 reflection basically inverts the z coordinate. It multiplies the z coordinate by -1. So that was the matrix for this operation. And then for the C3 operation, or I'm sorry, for the C theta operation about x3 axis, the matrix operator was cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, 1. And if you multiply these two matrices together, you're going to get cosine theta, sine theta, 0, minus sine theta, cosine theta, 0, 0, 0, minus 1. Okay, so this would be the matrix representation for the improper rotation by a angle theta about the x3 axis. Okay, and of course you can derive the matrix for the operator about any other axis by just cyclic permutation of the axes. So if you relabel, instead of having the x3 be -1, if the x2 is -1, basically, that you would get. Well, I'll just draw you an example. So the improper rotation about the x1 axis, that would be -1, 0, that would look like this. So basically I've just moved everything, so each element of this matrix, I've moved it down one row and over one column. And then I end up with this matrix here. Okay, and finally, let's look at the one last operation that we need to look at. That's the identity operation. And as you can probably guess, the matrix representation for the E operator is just going to be an identity matrix that leaves the x, y, and z coordinates unchanged. Okay, so just to give you a concrete example, if you had the water molecule with x3 pointing this way, x2 pointing this way, and x1 coming out of the plane of the page, right? And then you have a water molecule. Then the point group, as I mentioned before, is C2V. And the matrix representation of that point group, you could represent this point group using symmetry operators like we did before, but you could also represent this point group using a set of matrices under the combining operation of matrix multiplication. And then the elements of the group would be the matrix representation of E, the matrix representation of C2, which is, okay, the cosine of 180 degrees is -1, sine of 180 degrees is 0. Right, so this would be the matrix representation of C2. Then we have the matrix representation of the sigma 1,3 operator, and that's going to multiply y by -1.